Hey, hi, good evening, everyone. So sorry for joining a bit late. So I hope my voice is audible. Would anyone please confirm? Yeah. Okay, so today is, the core objective of this session is to revisit the concept of back propagation from a different point of view. It's not completely different, but just to see how things are related. So, in case if you want to write your own code for any neural network, then what will be the general approach? And I am going to discuss things that are not, not covered in the lecture. A bit about matrix dimension, all these things. Um, Let me share the screen. Okay. So I hope the screen is also visible. So some of you might already, have some good familiarity with feed-forward neural network. But anyhow, I'm going to start with a feed-forward neural network that is fully connected layers, and then show you how to build things, from there. Okay, so that lays the foundation for all different types of neural network that we have seen so far. So I'm starting with that. Again, to keep things simple, I'm going to consider, though you ask for some complex network, complex problem. So I think the core ideas can be illustrated using simple network. Once you understand them clearly, right, or thoroughly, without any doubts, then it is not that much difficult to extend it to complex network. Okay, of course, if you feel any difficulty, in extending the concept to complex network, please feel free to, you know um, post your steps in the discourse in case when you are developing or writing back prop from the scratch. Okay, so let's start with a very simple network. Let's say I have three inputs. Okay, that's x1, x2, and x3. And let's say I have three neurons in the first hidden layer, and then two neurons the second hidden layer, and one neuron in the output layer. Okay, and of course you know how things are connected, so I'm just going to partially connect all these things, but I hope you already be aware of all these things. Okay, and then this output is connected with this one. Finally, somehow all these things are connected. Okay, and we have the final. By the way, so is that readable? I mean, whatever that I write on the board. Okay. Okay. So the first thing is, we know that the neuron is composed of two parts. So it is always the best practice is to think of each neuron is composed of two parts. One is the linear part, the other one is the non-linear part. So you always divide this into two halves. Okay. Again, to keep it makes things simple, especially the calculation simple. So in all the neurons, I have a linear part, and with respect to the lecture, we follow the same notation: A1, H1, A2, H2. Of course, I'm kind of, when you have so many indices, okay, to denote I, J, K, and the layers, then things will get confused. So I'm going to, drop the indices once if I feel the indices is kind of constant, or it could be inferred from the context. Okay, you can also do the same whenever you feel, you are dealing with multiple uh, indexes. Okay, so forward prop is so straightforward, so we don't even need to bother about so many things. But before doing the forward propagation, since we are going to deal with dimensions especially, so let's make some assumptions. Okay, so the assumptions in the sense, my x is going to be a column vector. Okay, so when this is capital X, again for convenience I'm writing as x. Okay, it's going to be, the input is going to be a column vector. So in this case, it is going to be R3 by 1. Okay. And I'm going to represent the weights as a matrix, and row of the matrix denotes the weights for a individual neuron. Okay, that connects the input with the neuron. Okay, so the first row is actually the weights for neuron 1. How do I denote that? Maybe let me denote this as, okay, again it creates confusion. Just take this pictorial representation. The row of the weight matrix represents the weights associated with the first neuron. Okay, despite whichever the layer, this is going to be the convention. Okay, and then similarly we have bias, that is once again it's going to be a column vector based on the number of neurons in a particular layer. It might differ. Let's say it might be some m by 1, but it's just a column vector. Okay, so this is the convention we are going to follow. So keeping this convention, then we can compute the forward prop. That is straightforward. So again, while we compute the forward prop, you compute the linear part first, and then compute the non-linear. Okay, so even though you can compute these two things together, but it is always good practice to compute the linear part first. So the linear is, let's say I have a weight W1 that multiplies X, and then I'm adding a bias B1. Okay, and we could also keep track of the dimension in mind. Okay, and then the nonlinear part is H1, which is sigmoid of A1. So sigmoid is, in general, it could be any activation function, but I'm using a sigmoid. And similarly, we have A2, which is W2 times H1 plus B2, and then H2, which is sigmoid of A2. Okay.
Sorry, Arun, there is a problem, I think. The row of every W corresponds to only one neuron, right?
Yes, only one neuron.
And X is a column vector.
Yeah, it's a column vector.
So W1 in this case has to be a 2 by 3 matrix.
It should be 3 by 3 matrix.
No, W1.
W1 is the weight that connects input to the first hidden layer, right?
Oh, I see. You have two hidden layers. Sorry, I somehow
Yeah.
forgot that.
Yeah. So maybe I can use W0, but
No,
that's, I
sorry.
think.
I assumed that we only have one hidden layer.
Okay, so W1 and W2, and then this is W3. Okay. So we have this H2, which is equal to sigmoid of A2, and then finally we multiply the output with the, anyhow, for convenience we keep things simple. So let's say A3 is equal to W3 H2 plus B3. Okay, and then finally we have an output. We denote this as, in general, it's all right to y hat, which is H3, which is sigmoid of, again, to keep things simple, I just consider a sigma neuron instead of softmax with multi-class classification. The things are generalizable anyhow. Okay. So the forward propagation part is quite clear. Okay, so we don't. It is not that much difficult. It is simply matrix vector multiplication altogether. Okay, we keep repeating this process for each layer. Then finally we end up with the prediction. Okay, and once we have this prediction, then we have to pick up some loss function. Again, here I'm picking up usual mean square error loss. Okay, let's say I have loss L, which is equal to, I am going to use only one sample, so I am using this. Okay, y hat minus y whole square. So far things are quite simple. There are no issues. So the problem is to compute the gradients for the parameter. Okay, so I need to update what is the core objective. The objective remains same throughout the entire deep learning, right? So we always try to find the gradient for the weight vectors, which means I want to find gradient for W1 and then gradient for W2 and then gradient for W3. Similarly for B1, B2, B3. So this is a gradient. So how do we compute the gradient is the question. So to compute the gradients, we have n number of methods. And for deep networks, backprops works well. Of course, we have LB, GF as something very second order methods also, but here we are going to focus on only backprop. Okay. And the objective is also clear. Okay, let me delete this. So So to illustrate the core idea, what I'm going to do is anyhow, if I show you how to compute the gradients for W1, which is all the way, you have to keep backprop all the way up to the first hidden layer, okay, all the way up to input, okay. So the entire process. So to keep, that's why I'm going to compute the gradient for W1, okay. So gradient for W means, so we are computing the gradient with respect to loss. No matter where your parameter resides, what we are trying to calculate is the gradient of the parameter with respect to the loss. That's our ultimate goal. Okay, so I think this space will be suffice. So our end goal here is to compute the gradient of loss. So again, the abuse of notation. So I'm going to use dou L by dou W, even though we have to use the enable operator. Okay. So this is our objective and we know how to compute that, right? So how do we compute that? So typically when you just forgot about all the things we have learned. So if you really want to find that, we start off with this, right? For some reason, since we are keeping track of the dimensions, things will change a bit. So we are going to use the chain rule, but now I'm going to use the chain rule by reversing the order. Okay, so this is the case. So in order to match with the dimension, you will understand why that is the case after I demonstrate how the dimension works. Okay, so anyhow, we have to start with the final loss by computing the final loss, which is, I think this space is enough. So I'm writing this as, I have to first compute the loss with respect to the output. Okay. First, I need to compute this quantity. That's where I start. Okay. So this answer depends on the loss we use, but let's don't bother about that. And then we compute how the y hat changes. Okay. With respect to whatever the input to this one. So the input to the y hat is A3. So I need to compute how y hat changes with respect to A3. Then I have to compute how A3 changes with respect to whatever the input to that is H2. Then I have to compute how H2 changes with respect to whatever the input to it, which is A2. Then this process is repeated. We just keep repeating. Then how A2 changes with respect to the input to it, which is H1. And then how H1 changes with respect to the input to it, which is A1. Then finally, how A1 changes with respect to W. Okay, so we are going to end up here. So this is where we need to stop. Okay, so you can see that the computation starts from here, then we can keep on multiplying. So this equation remains same no matter which weight you pick up. Okay, you will end up writing the same chain rule in the reverse order because we are now focusing on the dimensions as well. So this part will not be that much difficult. So let's focus each one of these terms so that we understand how things work. So I picked up this example so that there are scalars and vectors. I mean, we compute the gradient with respect to a scalar, and also we compute the gradient with respect to vector, and also with respect to the matrix. Okay, so that we can see how things works, from the big picture. So I'm just going to hide this. Okay, so let me first focus on the first quantity, which is, even though it's trivial, since it will be helpful to talk about this once again. So we know dou L by dou y hat. Okay, remember in this case, in this specific case, my y hat is a scalar and the loss is also a scalar. So I am taking a derivative with respect to a scalar quantity. Okay, so the numerator is a scalar and the denominator is also a scalar. So that is quite straightforward. We don't need to explain on it. So it turns out to be 2 by 2 y hat minus y, which is simply y hat minus y. Okay, so I need not to and I'm not putting any specific numbers here, so that doesn't matter, right? So numerical examples you can simply work out, because after you computing all this partial derivation, you end up with some simple equation where you have to just plug in the numbers. So I don't want to waste the time on calculating all this matrix multiplication, because it is going to take some time. So I'm just going to leave up with the final equation. So you just, now we have computed this term, so I would have some numbers, right? After computing this term, I end up with some number, so I just plug in that number for this entire term, and then I will focus on the next step. Okay, so the next step once again is y hat do y hat by do a3. So a3, of course, y hat equivalently it is h3, but okay, that is understandable. So in this case, once again, the y hat is scalar and a3 is also scalar, because it's not multi-class classification. So you can see a3 is also a scalar, the linear part. Okay, so derivative is simply an activation function. It's a sigmoid activation. So once again, we can write the derivative of the sigmoid. So I'm going to keep this as sigmoid dash, okay, of a3. So whatever the input to the sigmoid, so that is where you evaluate this derivative. Okay, so you would have calculated this a3 in the forward prop. You will use the same value here when you compute the back prop. Okay, so I'm going to use the sigmoid dash of x, even though the equation for it is sigma of a3 into 1 minus of sigma of a3. So based on the activation function, you will have the respective equation. So you don't need to, we don't need to bother much about the derivative of the activation function. Now we have computed the second term, and we would have multiplied these two terms now, right? After I have some number for this one, now I would have computed this, and then I multiplied these two. So let me put dimensions here. So it's 1 by 1. It's also 1 by 1. So after multiplying this, the result will also be 1 by 1. Now let's focus on the next term, dou a3, which is a scalar, and dou h2, which is a vector. Okay, so if you, again, just to show you why, so we can see that now I am computing the derivative of, how the a3 changes when h2 changes. H2 is in fact a vector. Okay, so my numerator is a scalar, whereas my denominator is a vector. Okay, I am computing dou a3 respect to dou h2. Okay, so this time this is a scalar quantity, this is a vector quantity. Okay, so we can, again, just to have some idea, I'm just expanding this. Okay, since this is a vector, I'm just putting h2 0, h2 1. Okay, I'm not including the index for the layer. I don't care about that. Okay, so I know the number of elements in this vector is 2, so I'm just using h2 0 and h2 1. So so when we encounter situation like this, okay, of course in this case the numerator is scalar, the denominator is vector, but in the next case the numerator will be a vector and the denominator is a vector. So when we encounter scenarios like this, okay, so how do we compute derivative? So typically, there is a debate whether which layout to follow, but I am also seeing denominator layout is quite okay. You can follow anything you want, but I'm going to follow denominator layout. Okay, so what do I mean by this denominator layout? So when I compute the derivative for this, okay, here we have only one quantity, a3. So what I'm going to do is I'm just going to compute dou a3 by dou h2 0, and then dou a3 by dou h2 1. So it seems quite natural in this case. In the next step, you might see, when we encounter vector by vector, the numerator we have vector and the denominator in the vector, then this layout makes sense. Okay, so you have to be consistent in following a particular layout. If you are following denominator layout throughout the computation, you have to stick with the denominator layout. Okay.
Actually, it's not clear what this is. I mean, this is one way. Is there another way of doing this?
Yeah,
Like
in this case,
denominator layout versus what?
yeah. So in the denominator, I have a column vector, right? So of course I can put some say. So in the numerator, I have m elements. In this case, I have only one element. In the denominator, I have two elements, 2 by 1, right? So if I follow the denominator layout, then it will be 2 by 1. So the size, let's say if I generalize this, this has m elements, this has n elements, then it will be m by n size. So when you compute derivative, of course, in the next step, you might see the things clearly. So in this case, it doesn't make much,
Because this is the only option we have, no? In this case.
Yeah, in this case, the only option is this. So you can also argue, right, since you are just computing derivative with respect to a scalar, you can put things in a row order, right? Why should I follow this
Oh, I
column
see.
vector?
So I mean, what you mean is whether the gradient should be a row vector or a column vector.
Yeah. That's both are the gradients, by the way, whether you represent it as a row vector or column vector.
Correct. But it would be easier to keep it in whatever shape the actual parameter is.
Easier, I mean, the consistency matters. So you can keep it in either column, I mean, in this denominator layout or numerator layout. Both are easier. But since, the matrix multiplication is not commutative, right? So it will, uh, you know, brings in a lot of wrong, what do I say? Confusions or miscalculations if it change the layout. If you
Anyway, I
stick,
think I suspect this is not really crucial, right? Like we can just stick to this and compute
yeah,
forward.
it's if you stick with one layout format, then it's not a problem. If you just follow this consistent, uh, you know, approach throughout the entire computation, if you stick to the denominator layout, then there won't be a problem. But for one term you use denominator, the other term you use numerator, then it will end up messing things. And also while writing program, right? So it won't raises any this dimension mismatch error if we be consistent. If it raises dimension mismatch, of course we can fix it by referring to why the dimension is mismatching, and we can change it accordingly. But to have this, to avoid this unnecessary sort of errors, then we need to follow a particular format.
I have a one here doubt, sir.
Yes.
So what we do that here, the numerator is scalar and the denominator has the some dimension. So
Yeah.
whenever we differentiate, is that format of the output is the internationally fixed or it is the choice of our, because that
No.
like what we have written that if I divided by the column matrix of the scalar, output is the column matrix. So it is our choice or the internationally some dimension is fixed for that.
No, the community is divided into two groups. Since logically, you can follow any two. Either you can follow keep the gradients in a column as a column vector or a row vector. As long as you, you have two options which are inevitable. Both are right. Then the community divides between the two. One follows the denominator layout and the other follows numerator layout. But they have to mention which layout they are following for others to, understand their algorithm.
Okay, so
There is no kind of, because we can't impose standard here, right? Everyone has to follow the denominator layout.
okay, I have seen that this thing in the Wikipedia, they mention it as the row matrix.
Okay, but you can, when you refer to the different books, right? People, most often I see people follow denominator layout, but there are cases maybe in physics based on the domain, right? So the gradient can appear anywhere. So based on the domain, they might have follow some format. In deep learning, I always see denominator layout.
Okay, okay.
Yeah, Rakesh, I make it available. Oh, okay. So I think I have this. I must have shared under YouTube live session. Okay, so all right, I guess. Okay, so here we know the answer, right? So I mean, computing this derivative is also not difficult. So this is once again, what is dou A3 by dou H2 0? I think it's not anyhow. This might also cause confusion. So we know how we compute A3. So what is A3? A3 is W3 times H2. I'm just expanding for this term. So for the next term, I'm just write the answer directly. Okay. So if you think about this, we have W3. Okay. I think how many neurons we have there? Okay, so it's very simple. We have only two weights. W30, let's call it as, we have only two weights there. So in the forward prop, we use two weights, W30 and W31. And then we again, we follow the same, right? So we place the weights in a row order. And then we multiply it with the H2, which is again H20 and H21, which are output from these neurons. And then we add the respective bias. So here, so the bias is for this neuron. So it is, yeah.
Hello, sir. I just joined a few minutes before. Can you tell which topic is going on?
I am talking about computing the backprop for a simple neural network. Then I will extend to BPDT.
Okay, okay.
Excuse me, sir. Sir, you have mentioned in the left side that A3 is a scalar.
Yeah.
But in this equation, like A3 is equal to W3H2 plus B3. So if H2 is a vector, then W3H2 is also going to be a vector.
So it's a dot product, right? So we have only one neuron in the output layer. So it's a row in times column. So it's a dot product, right?
So like my doubt was if W3H2 right hand side is a vector, then A3 should also be vector. Can't we say like that?
No, we can't, right? So essentially what we are doing is that if you focus on a single neuron, the single neuron has an m weights, and if input is m, then we simply compute the dot product. If you have only single neuron, then it is always going to be a scalar. The input to the neuron is going to be the scalar.
Okay, sir, got it.
Yeah, so that's why, this sort of confusion is very common. That's why I, break down the things on your own, expand it and see the pictures clearly. Okay, no matter how many times people are, no matter how many videos you watch, unless you write down on your own and expand the things, then you could avoid these sort of confusions, okay, which are crucial for exam. Of course, for conceptual understanding, it's fine. If you make a mistake, you can go back and fix it. But from the exam perspective, you need to be very, clear. Okay. So here we want to compute. Of course, you can once again write things clearly to avoid confusion. W30 H20 plus W31 H21 plus B3. This is what we have. Okay. So now I am computing A3 with respect to H20. So what I have is I'm going to have only, if I take a derivative, okay, of A3 with respect to H20, I will have only W30. Okay. Then all these terms disappear. Similarly, when I take A3 with respect to H21, then I will have W31. All the things will become 0. So you can clearly see that this entire matrix, right? I mean, dou A3 with respect to dou H2 is equal to W30, W31, which is equal to W3 transpose. Okay, so it's quite straightforward. Okay, so I have W3, which is a row vector during the forward prop. To compute the gradient for it with respect to the input, then simply it becomes W3 transpose. This is the case if you have followed a denominator layout. If you have followed the numerator layout where you have placed the gradient as a row vector, then it remains W3. Okay, so this transpose things is the only thing that, if I'm not wrong, okay, that might change when you switch from denominator to numerator layout. Okay, so in denominator layout, if you have W3 transpose, if you follow numerator layout, then it becomes W3. Okay, but anyhow, do not try to memorize this. You can see this clearly just by expanding the equation. Okay, so
No, I think, sorry, I probably understand this is an irrelevant point, but could you check if W3 was originally a column vector? I just did some calculations and it turns out that W3 is actually straight away a column vector only. Like the way we have defined our x's, the initial.
no,
If,
right. So
if x happens to be a column vector, then W3 also should be a column vector. That's what I'm getting.
no, yeah. The thing is that for this neuron, right? Let's say I focus here. For this neuron, things are connected through. Let me say this is W00. This vector is W01. This vector is W02. Right? I place these three weights as a row in a matrix, weight matrix. Here I have only one neuron and I have only two weights, right? W30, W31, and I place these weights as a row vector, right? So I stack the weight for each neuron as row in a matrix.
For each neuron as a row.
Yeah, the weights for each neuron, right? So
So here there are, since it's a 2 by 1 thing. So if each neuron becomes a row, then it's a column vector, right?
I don't know. I mean, what is okay?
Anyway, not critical right now. Please. If
It's
somebody
not
else
critical,
could,
but no, this is the starting point, right? So that's why I'm expanding
I mean,
things.
if the dimensions end up being wrong, you just transpose again. But if somebody else could verify this, that will be great.
Okay, so is that clear to everyone with how W becomes W transpose? Or do you want me to explain it a bit? If you want, then you just press thumbs icon. Not icon. What is that? Emoji. Or if you understood, then I can just move on. So whenever I ask this, please be frank to yourself, right? So if you miss things here, then like when you compute gradients, of course, you end up missing things.
Can we do one thing? Can we try this numerator layout? Let us expand and let us see like
No,
how it
that will
works.
mess up my thing, right? So I have some structure and I mapped everything to that. So if I switch to numerator layout, I mean, I can show you what happens if I switch to numerator layout here, but not throughout the problem. Then I
Yeah,
will.
just to compare here on.
Okay. So the in numerator layout, what we do is here we are computing dou A3 with respect to this dou H2 and we are following this column, right? So the input is a column vector, the output is a column vector. So H2 is also a column vector. Now I need to compute the gradient with respect to gradient of A3, which is a scalar with respect to a vector. So which means I need to compute the gradient with respect to each element in this vector. So gradient in itself doesn't matter. So you can compute, which means, right? I delete this, by the way. Okay, so what do we mean by computing gradient means? So I'm computing how this particular A3 changes with respect to H20. So which means for that I take a partial derivative. I compute dou A3 by dou H20. I want to know this info. Similarly, I want to see how A3 changes when H21 changes. So once again, I can compute dou same quantity A3 and dou H21, right? So how do I pack this? I have two. So to make sense of it, we pack these two values into a vector. So when you pack this, you can either pack this as a row vector, okay, or you can pack this as a column vector, right? The choice is yours. So in the previous case, I followed the column vector. In this case, there is no issues. I can follow the row vector. So if I put these partial derivatives as row, okay, or elements of a row vector, then I say now we are following it numerator layout. Okay. So if I do so, then what happens? So if you take the derivative for this, the things will change, right? Now W31 comes here, right? So the values are not going to change. If I compute A3 with partial derivative of A3 with respect to H2 0, okay. So if you take A3 with respect to H2 0, the W30 is the answer. So I can write it down. Similarly, if you take derivative of A3 with respect to H21, W31 is an answer. So if we follow a denominator layout, I put W31 here. If I follow numerator layout, I put W31 here. Okay, this is simply just packing these values, packing this partial derivative, as a row vector or a column vector. So if you do so, then you can see my weights are arranged as a row vector. So when I compute the gradient, I follow the same. So there is no difference. So it is going to be simply W3. Okay. But if I follow a column vector, it's just W3 transpose. Okay. So in fact, this is not that much. I mean, it is not a thing that will, give you a wrong answer. Even if you forgot to, if you mess up things when you compute, while you manually compute everything, you can see the dimension won't match, so you can properly switch it, right? But when you write the code, then things will get complicated if you don't follow a particular format. Let's spend more time on this if you have, if you have struggle understanding this concept. Because once again, I'm stressing, since this is the first step, then we should be, good at least have some good grasp on these steps. Is that clear? Or
yes, it's better to little more explore here, because there is a 2-3 possibility can come here. Here we are dividing differentiating with respect to H2. So
yeah.
So what's happened, W3 we are taking as the constant. So A3 in the better way we can write the W3 at H2 plus B3. So at means it is a looks matrix multiplication, and the W3 is the 3 by 3 matrix, right?
W3 is not a 3 by 3 matrix. It's a 2 by 1 matrix. 1 by 2 matrix.
1 matrix.
No, 1 by 2 only. Yeah, I'm wrong.
Okay, so if so there is a both vector is there, and both vector is multiplication, matrix multiplication, and we are differentiating with respect to vector. So dimension wise, if we will discuss that, and this will clear the most of problem even in the RNN. So if we change the dimension, let's say that if independently I'm telling W3 I keep that 3 by 3 matrix, and H2 I'm keeping the 3 by 1 matrix, and then I'm differentiating with respect to H2.
Okay, so that's what we do in the next two terms. Maybe once I illustrate that, you might get that, because in the next time I have to take the derivative with respect to vector. Here it's a scalar.
Yeah, vector with respect to vector, that would clarify.
Okay.
Yes, so if we will expand, if we will explore a little bit vector to vector, it will clear everything.
Okay. So now we follow the denominator layout. So we have W3 transpose. Okay. Okay. So let's stick to that.
And one more thing, because you said like community is divided over numerator layout or denominator layout.
Yeah.
Is there any like dominance of any like layout?
No, there are some subtle differences, maybe very specific. It might change based on the application as well, based on the implementation. I'm not sure. We can't simply say denominator layout is always best in some scenario, or numerator layout is always best in other scenario, because it is once again boils down to a design choice. So I'm not aware of any such things where the numerator layout dominate particular area, denominator layout dominates particular area for some reasons. Maybe it's a design choice, but I'm not sure whether any specific reasons are associated with this for this domination.
Arun, I think that this is not really it doesn't seem like it's a big problem. Like you can choose anything, and ultimately what happens is if your dimensions are mismatching, then straight away your code will crash and it will tell you that they are mismatched. And when that happens, you just have to go and transpose one of the matrices which are in the line somewhere, right?
No,
So I think that by itself is not really the crucial thing here. Am I underestimating this issue?
No, it's, I mean, when you develop a framework, you have to ensure that, improper dimensions are.
Consistency is definitely required, but otherwise, obviously, like the code won't work.
No, the code does work. I mean, even if you mess up with the dimension, as you said, you can go back and fix. You just take a transpose and then things works. Then you just move on. It is not going to affect the end result if you are conscious about how things are getting multiplied. It raises a dimension mismatch error, then you go and see, and you know that the vector has to be multiplied in this way, so you take multiplication and just move forward. You can fix it.
But I'm thinking, sir, like that in even the Cartesian coordinate system, the system is designed such a way that we are only can choose the 2 dimension, but we are not allowed to choose independently third dimension. Third dimension must be follow some rule, the cross rule to choose that. So similarly here, there must be the one rule, because if I'm talking to the vector by vector, it is very simple scenario. We can think mentally about the dimension, but try to understand the situation where that I'm giving the numerator like a f multiplication g multiplication h, where the f g h is the matrix, and the p and q dimension matrix, and 3 matrix multiplication, right? And the f g h is the function of x, and the x in denominator itself is the some row matrix, column matrix. Then it will be completely hard if I don't follow the rule to solve this problem.
Yeah, I mean, that's anyhow boils down to this consistency. You have to follow some, ensure that the consistency, especially when you design a generalized framework or you're designing some API for some user, you have to keep things in mind. But once again, for simple toy problems where you work out manually, you can follow. I mean, even if you make an error, you can fix that.
Okay. Yes.
And I believe, or I suppose, like there must be some principle behind choosing particular layout.
No,
I don't know. Yeah,
but even I have referred some books, but whenever I follow people, either they give you an option. They said, I am going to follow denominator layout. If you wish, you can follow numerator layout. That's what I have seen. They don't talk about this is the difficulty you face. You follow numerator layout. That's why I'm following denominator. I haven't seen any such reasons by the authors.
Okay, so we can move on, I suppose.
Yeah. Okay, so here we follow this. So W30. The key takeaway is that if I follow denominator layout where I am placing my weight vectors as numerator in a weight matrix, as a row vector in a weight matrix, then when I compute the gradient with respect to the input, then the gradient is simply the transpose of that vector. Okay, so here we have only vector. If I have a weight matrix, then matrix will be transposed. Okay, so let's see how that works for the next term. So where you might get some better picture. Okay. So now we have computed dou A3. Maybe I use different colors. We computed this. Okay, and the dimension turns out to be 2 by 1 because the gradient is now column vector, so it's a 2 by 1. Okay. So now next I have dou H2 by dou A2, where dou H. Okay, let me write it down.
Is it by A2 or A3?
Which one?
The next gradient. Could you scroll up to that expression, the chain rule?
Yeah.
Okay, got it. Yeah, sorry, that's right.
Yeah. Okay, so we have next dou H2. So this is the reason why I skipped this. I mean, introducing these dimension things in any of the live sessions, because anyhow it brings up a lot of confusions than clarity. But once you understand all these things, then things make sense. But okay, let's move on. So I have dou H2 by dou A2, right? I know. Oh, sorry, it's not. So I know H2 is a vector. Okay, and by the way, this is simply passing the vector through an activation function, but which is kind of element wise operation. But again, from the matrix operation, we consider this as taking derivative of a vector with respect to a vector. Okay, so A2 is a linear part. Once again, it's a vector, and H2 is the output from that nonlinear function. Okay, so we know that. So if you just expand this, we can see do H2 is how many elements are there in the H2? There are two elements, right? H2 0, H2 1. Similarly, how many elements are there in A2? I have to use Nebula, but once again, it's okay. Okay. Now we have to compute the partial derivative of H20 with respect to A20 and A21, and H21 with respect to A20 and A21. Once again, the problem rises. How do I place things? Okay. So if we once again follow the denominator layout, what really happens is that the size of this one is 2 by 1. Unfortunately, both the vector sizes on the numerator as well as in the denominator are same. This is also 2 by 1. So the result will be what will be the result? So it will be 2 by 2 matrix.
2 by 2.
Okay. So the thing is, now I take the first step is clear. I can take the derivative of H20 with respect to A20. Okay. So here, what should I do? Whether I have to compute, I can do one thing. I can take the derivative of H21 with respect to do A20. This is one way, right? Or I can place the other element as well here. I can place this element as well. I can compute H20 with respect to do A21. This is also fine. Okay, once again, it is placing this partial derivative, whether I have to place it here or as a row vector or a column vector. So now we are following a denominator layout. What does that mean? So one pictorial, you just forget about M, N, all these things. One intuitive way you can follow is, see, I have placed the element as column A20 followed by A21. So in all the numerators, I have only this do A20. Okay, so here I have the first element is I'm taking derivative with respect to A20. The second element I take H21 with respect to A20. So if you take the entire numerator, the partial derivative is with respect to A20. Okay, then I repeat the process. I take the derivative of H20 with respect to A21, then H21 with respect to A21. Okay.
Okay, this actually makes it clear. So if we had used numerator layout here, we would be getting the transpose of this matrix.
Yeah. The matrix will get transposed. So you can, again, an intuitive idea is the denominator layout is preserved. You can think of something like this. Okay, do A20 and do A21, which follows this column vector thing. But H20 is kind of, now it becomes a row vector. Okay, even though H20, H21 is a column, but when I follow denominator layout, I ensure these partial derivatives are collected by following a denominator layout. So in the denominator, now I have a column vector, so I am following the same thing. Okay, but if you get confused by this, you just ensure that you have A20 here, A21 here, then you follow everything. A20 here, A21 here. If you have other element, then A22 will be next row, forms a next row vector. Okay, so of course, when you work out everything, you can see things clearly. But at least does it make sense now? So what denominator layout is? Putting an exact definition is quite difficult, by the way, unless I look into the Wikipedia. But
So will you do one thing, sir? For that your derivation, can you follow that your pattern?
Sorry, which one?
That the dimension about that. So
Yeah.
if we will follow that only one, it will be the mindset will be with one set. So
Yeah, I'm just following this denominator layout only now.
okay. So
So I'm going to stick with that throughout this computation.
okay.
Okay. Okay. Now, if you compute, when you compute H20 with respect to A20, of course, it's simply a sigmoid function, right? Because remember, I have a neuron here. The input is A20. You pass it through a nonlinear, then you get H20. So H20 depends on A20. So when you take a derivative of that activation, then you will end up with the derivative of the activation function, which is sigma dash of A20, right? And what about the derivative of H20 with respect to A21? Anyhow, it's not connected in this way. Okay, so A21 goes into the next neuron. That's what the A21. Then it only influences H21, not H20. So this becomes 0. Same thing goes here, becomes 0. Then we have this sigma dash of A21. It's 2 by 2 matrix. Okay. So this is going to be the case for all nonlinear activation functions. So whenever I pass an element through an activation function, the output of the activation function depends only on the input to that activation function. Okay. So even if my network contains some m neurons, then the derivative will contain a matrix where only we have diagonal elements. The matrix is going to be diagonal. Okay, so this is true for all the case. Okay, so when you pass an elements through an activation function, while you compute the gradient during backprop, you will get a diagonal matrix. That is bound to happen because of that's how things are computed during forward propagation. Doesn't make sense why it is always going to be a diagonal matrix.
I think for the softmax, it will not diagonal, or it will be in the softmax case also.
Yeah, in the softmax also. So I remember I worked out in detail. So when I worked out in detail, it turns out to be diagonal matrix.
Because sir, softmax has that every term is containing the all term. So diagonal term may not be 0.
Yeah, I looked into that, but in my memory, I remember this when I computed the partial derivative for the softmax as if I'm computing this entire matrix. So it turned out to be diagonal. I check it.
Okay.
Yeah, you can also check it on your end, but if I check it and found, then I put it a message in the group.
Okay.
Okay. So of course, since it is diagonal, we can arrange. I can take the entire diagonal and keep it as a vector, and I just do element-wise multiplication, right? So okay, is that clear now why it is a diagonal matrix? Are you able to understand this denominator layout convention when you compute a gradient of a vector with respect to a vector, and then how a matrix emerges? And for this specific case, the matrix is going to be a diagonal matrix. Does that make sense?
Yes, sir. So you can say one thing here, sir. Instead of since we know that it is the diagonal matrix, right? So we need not to compute that the entire matrix. We can directly column wise we can compute and we can make the entire matrix diagonalized.
Yeah, that's what the computational graph does. The computational graph keep tracks of the dependency, then it never computes. This is not how actually backprop works in the framework. It creates a computational graph. It simply eliminates all this unnecessary computation, Jacobian product.
So here we saw that using Jacobian type of thing, and we came to know that okay, it is diagonal. But if we somehow know that we don't need to do Jacobian matrix, right?
Yeah.
Okay.
Okay. So now we are fine with these three computation. So things are making sense now. For examination, you can follow either this approach or because it's going to be a very toy example. So it doesn't matter whether creating computational graph or follow this matrix approach. But in general, be aware that people are not implementing this approach. They create a computational graph. Okay, so now I computed this term, which is dou H2 by dou A2. which turns out to be a 2 by 2 matrix. Remember, I know this 2 by 2 matrix is a diagonal matrix. What happens if I multiply a diagonal matrix by a vector, by a column vector? What happens? I have a diagonal matrix, I have a column vector. What it does to a column vector?
Just keeps it like that.
Yeah, it simply scales,
Only
right?
scales, yeah.
Okay, so that it's a pure scaling operation, right? So that's why we know it is going to be a scaling operation, so we don't need diagonal matrix. So we keep things, it's simply an element wise product, right? So that's what people do. So we did, when you write a backprop code, you just end up taking an element wise product between the vector and this one. Okay, fine. Now the next term is a2 by h1. And before moving on to a2 by h1, let's look at what is a2 and h1, because we may have forgot. Okay, so a2 is a vector and h1 is also a vector, but this time the dimension is changing, right? So I have a2, which is a column vector with 2 elements, but h1 is once again a column vector with 3 elements. Okay, so now maybe you get a better picture. So if I make any mistakes, please point that out. Okay, now I'm going to take this dou a2 with respect to dou h1. Okay, and of course, without computing the things, you can tell me the answer. What will be a2 by h1? I mean, you can kind of make a correlation. In the previous case, that becomes W3 transpose. So what would happen? I mean, in this case now,
W2 transpose?
yeah, it simply becomes W2 transpose, right? So let's see, is that the case? Okay, again, these things are quite necessary, so I'm just expanding this. So we have 2 elements, a2 0 and a2 1, whereas for h1 I have 3 elements. Okay, again h1 0, h1 1 and h1 2. I'm dropping the index for the layer. Okay, oh no, sorry, not for the layer. Okay, so now if I follow the what is that, denominator layout, can you tell me how do I write? Just tell me the elements row wise. So the first element is going to be dou a2 0 by dou h1 0. What will be the next element along the row?
Dou a21 by dou h10.
Yeah.
Dou a2 0 by h11.
No. It will be row a21 by row h10.
Okay, so I think there is all of you think and agree. So I put a poll here. Approach 1. Sorry, the option 1. I'm just putting option as O1, O2. Okay, so the O1 stands for the next element is dou a21 by dou h10. O2 stands for the next element is dou a20 by dou h11.
It's hard to say, but I can tell that next row element will be row dou a21 divided by dou h10.
h10. Yeah.
And that's what I said. Why do you say it's hard to say?
Means
I mean, remain
02 is there, no? So
okay. So that's because we are following denominator layout, right? So it is going to be, I'm going to keep this as constant. So not as a constant, but many dou a21 by dou h10. So the next row is going to be, what is that? Dou
a20 by h11.
Okay. Yeah. So I mean, you understand the picture, right? So dou h11 and then dou a21 by h11. Then the next element is going to be dou a20 by dou h12 and dou a21 by dou h12. Okay. So what is the size now? It is
3 by 2.
Okay. So I have 3 by 1 matrix in the denominator and 2 by 1 vector in the denominator and 2 by 1 vector in the numerator. So denominator layout means the first dimension is going to be whatever the size of the denominator. So it counts to be 3 and then followed by the numerator 2. If it is a numerator layout, it's simply a transpose. It is going to be 2 by 3. Okay, does that make sense? Maybe. Okay, so you will see these things clearly. So now we know A2 what is the derivative of A20 with respect to H10? If you just, this is simply a linear equation, right? Can you look into that and tell me the answer? What is dou A20 by dou H10?
W2 transpose.
That's the final answer, by the way. So the elements, individual elements. Okay, so you work out, you see that is going to be W2 transpose. Okay, so what is W2, by the way? So if you look at the W2, it contains how many row vectors? In
3.
W2, you no, how many row vectors? W2 contains 2 row vectors, right?
3, no?
Why it is 3?
Because it contains 3 neurons in the previous layer and each neuron contributes 1 row, which is
Yes,
which
sir.
was our original assumption.
No. See, we have 3. The output from the 3 neurons are multiplied by weights, right? So I have only 2 neurons in A2. So I will have only 2 row vectors, right?
Sir, there should be 2 column vectors because for the first neuron there would be 3 input weights that are coming.
Oh,
Same.
no, sorry, Arun, I think you're right. Yes, because every column is 1 neuron, is coming from 1 neuron, which means that every row corresponds to, was it 1 neuron or multiple? What was our original assumption when you look at that W that you have written earlier? So 1 row is 1 single neuron, right?
Yeah, so let me clear that up. I think skip repeating. Let's say I have only 2 neurons, right? And I have 1 neuron. So for each of these, I have weight W0 and W1. Okay, so what I'm telling is for this particular neuron, I am putting the weights as a row vector. So I'm putting the row vector. So now it is W0 and W1. So if I add another neuron here, then what happens? I add an additional weight, right? So for each neuron, we have associated weights. So if I have 2 neurons here, then I have 2 row vectors. If I add the third neuron, then I will have the 3 row vectors, right? Doesn't make sense because, I mean, if you look at closely, you can see that picture, right? So if I have 2 neurons, of course I have to use some indices W00 and W01. Okay, so this set of weights is for the neuron 1. For the next neuron, the inputs are going to be same. This is not going to change. For the next
Oh, I
neuron,
see.
the weight is
Yeah.
going to be W10, W11. So these are all the weights for the second neuron because the input is fixed, right?
I thought you meant that the rows correspond to the left side, not to the right side.
Yes.
Okay, got it. Then it's clear.
Okay, so let me delete this. Okay, so now, so even if you are, getting some difficulty in doing this, you just take some simple example, then you can simply figure it out. Okay. Okay, so
Here,
yeah.
yes. Here I want to just focus one more scenario. Dou A2 by dou H1 we have did, no? So next step you have written that A2 as the vector, like A20 and A21, right?
Yeah.
I don't want to think that way because suppose I don't want to think. I want to think another way. So
Okay.
A2 itself is the resultant of the W and previous H1, right?
A2, yes, it's
A2 is
multiplied W2 times H.
W2 at H1.
Yes.
So I want to think in that way. So instead of that, I want to write that notation. So in the first step itself, instead of dou A2 by dou H1, can you write, sir, that dou W at
Okay. Give me a second. So what do you mean? Yeah.
yeah.
In
So
which step you want to say? In this step?
first step, no. Before that, even.
Here.
Yeah, before that.
Okay. So
First
what do you
step
want?
itself, I'm writing dou A W dou in bracket
Okay.
W.
W.
Yeah,
Okay.
at notation means no W matrix multiplication. Yeah,
Okay.
H1.
Okay.
We can write this one A2 equal to same thing.
Yeah. Anyhow, it equals to the same thing. Of course.
Yeah,
That's
yeah,
it is the result of this.
yeah, and divide by dou H1.
Okay.
So directly we can say without even doing in the matrix in the depth, we know that upper dimension is solvable and below dimension is the H1 is there. No need to match the dimension. So we can directly say that W at H1 dou H1. So H1 will get 1. So we can say that answer is direct W.
No,
H
it's not. Why do you say that's the problem, right? So how do you say it gets cancelled? It's not
no
like
no W is the constant here.
it's
W is
constant, but it is arranged as a matrix. So the problem is there. You can't simply assume as usual. If I have y is equal to wx, where w is a matrix and x is a vector, then when I ask for what is dou y by dou x, then you
yes.
have to tell me with respect to whether you are following a numerator or denominator layout. Even
I'm
though I treat w as a constant, it could be w or w transpose based on the
Okay,
uh,
then I'm giving the logic, my logic. So see that W and the H1 is the somehow dimensionally matched. That's why it is here. So suppose take that W is equal to 3 by 3 matrix. Let's say that W equal to 3 by 3 matrix.
okay.
And the H1 is equal to 3 by 1 matrix.
Okay, it's 3 by 3. Okay, let me write down 3 by 3.
No, H1 is the 3 by 1 and W is 3 by 3.
Okay,
Yes.
so the result is going to be 3 by 1. Okay, let's skip
Yeah.
this and then.
And bottom is same as the 3 by 1.
Okay,
Now think that in the previous scenario you told that suppose W is the constant. So if there is a no matrix multiplication, I can think as that W is constant, so W will be the answer. But right now, since it is the matrix, we can say that W at dou H1 by dou H1. And since
okay,
dou H1 is that matrix 3 by 1 and the dou H1 is below is also 3 by 1, according to it will be the 3 by 3 matrix.
that's correct. But if you see that picture, you won't see why it gets transposed, right? Now the result is in fact transposed w. It's not w.
So I'm telling, since transpose happened because you have followed that denominator rule, right?
Yeah, that you can take it for granted
If
with
I
it.
follow the numerator rule, then transpose will not happen. It will be same come as the W2 only.
Yeah, that's correct. I mean,
Right?
here you could have written directly. I'm just expanding it, all these things just to,
Yeah.
once again reinforce the same concept.
Yeah. So
I'm
I'm
not telling you every time you have to do this. Once you understand, you can simply directly write it down.
yeah. So in the case I'm telling that I'm not using the denominator because I'm giving the priority of the numerator because as the internationally everyone gives. So I'm just giving priority numerator and I'm following the dimension of numerator. In that case, dou H1 by dou H1 will come unity matrix sim I, which is the 3 by 3, and W will be the W. So without even going that, I can direct. So it is coming the correct answer. So and the in that scenario, we are going to completely avoid that intermediate Jacobian matrix.
Yeah. So you want to keep w as w without doing any transposition if you follow numerator layout.
Using mathematical proof like that, the way I did. For example, the in the below, can you write equal to?
Okay, let's come back to that, Kumar. So, because I still not get into this RNN part, right?
Okay, yeah.
Maybe once you understand all these things, that's fine. Whatever that suits to particular, scenario, you can pick anyone you want. Okay, so I mean, now the picture is clear. So we have all the things we need. So only thing, the same thing will get repeated. Okay, so we just keep on repeating the same thing for every scenario. So now we have computed this. So the dimension is going to be, what is the dimension? It's 3 by 2, right? It's 3 by 2 matrix. And for this, what will be the dimension? Can you guess quickly by comparing this one and this one? H1 is of size 3 and A1 is of also size of 3. So it is going to be
3 by 3.
3 by 3. Again, it's a diagonal matrix, right? Because it's going through the activation function. Okay, so the things gets bit twisted here. So here now A1 is vector and W is a matrix. Okay, so then of course, if you take derivative with respect to, a vector with respect to a matrix, then the result will be a tensor. Okay, we don't really need to do this, but again, for the sake of completeness, I'm going to just show you how things works and see how things get connected. Okay, so whatever we did in the class, we end up with the same result. Okay, so it's dou W. So again, I'm just get rid of this index. So I have vector, and then here I have a matrix. So I have this, again, it's A0, let's say A1 and A2, 3 vectors. And then what could be the dimension of the matrix? So it's dou. How many elements were there? Can someone recall? Just make it. It's 3, right?
It's 3 by 3, so 0, 1, 2, 0, 1, 2.
W01, W02.
W0, 0.
Okay, 01. Okay, then W10, W11, W12, and then W20, W21, W22. Okay, so now what we can do is that, since once again we are going to stick with a denominator layout, which is of size 3 by 3, and the numerator is 3 by 1, so the resultant dimension is going to be whatever the size of denominator that comes first. So it's 3 by 3, and then the numerator is 3 by 1. Okay, it's going to be a tensor. So it's going to be 3 by 3 by 3 by 1. Okay, or essentially it's going to be 3 by 3 matrices. Okay, so that's what it says. So how do we go about it? Now you can think of the matrix is just a collection of column vectors. Okay, so now as we are following denominator layout, I'm viewing this matrix as a collection of column vectors. So what I'm going to do is that first I take derivative with respect to the first column. Okay, so if I do so, what do I get? First element is dou A0 by dou W00, and then the next element is going to be dou.
Same dou A0 by dou W.
No, it's dou A1 by, because I'm going to follow this, right? The
No, but then, aren't you getting rid of the denominator? What was that? Denominator priority?
Sorry, why?
Because it will be 3 matrices, each of size 3 by 3.
Yeah. Now I'm just focusing on the first column.
First matrix will be derivative of A0 with respect to everything in W. And then second will be A1 with respect to everything in W, but the shape of the W will be maintained, right?
No. That's not, because all this A0, A1, A2, this W00, W01, W02 influences A0 only, right? And similarly, the second row influences A1 only, the third row influences A2 only.
No, okay, yeah, I see what you mean, but that is incidental. If we were to actually go through the motion of properly doing this out, then you would end up with three matrices. First of which is do A0 with respect to everything in W, then do A1. Yeah, true that some
No.
of the columns might end up being zeros.
Yeah, but so this where things get a bit complicated, but you work out and see why I am following this particular approach. Okay.
Okay.
Now you form the matrix, but this time I'm taking a vector with respect to vector, the first column vector. So it is going to be dou A0 and dou A1 by dou W00, and then dou A2 by dou W00. Okay. And then the next thing, what will be the next? Same dou A0 by dou W10, dou A0 by, A1 by dou W10, dou A2 by dou W10. I know things are, either way, backprop is, you can follow whatever the approach you want, but this is also fine. The third row is going to be dou A0 by dou W. What is that? 20, and do A1, do 20, and do 2 by do W20. Okay. So quickly you can recognize that. Of course, similarly you have to take the derivative of the numerator with respect to the second column vector. You will get the second matrix. Then take the same for the third column vector. Then you will get the third matrix. Okay. So if you look at clearly, right, dou A0 by dou W0 is equal to x1, and dou A1 by dou W10 is also equal to x1, and dou A2 by dou W20 is also equal to x1. Okay, and then you can see A1 is not influenced by this W0. The rest of the element becomes 0. Okay, you can verify that later. So finally, what I have is, once again, I have a diagonal matrix x1, 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 where the rest of the elements are all 0. Okay, so this is one such matrix. In the next matrix, I will have x2, x2, x2. The next matrix, I will have x3, x3, x3. Okay, so you just imagine like that. Okay, we have the other matrix hidden behind this with all x2, 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 and then all 0, and then third diagonal matrix. See, still now this is simply x3, x3, x3 with all 0. Okay, so you just keep this in mind, and I will try to, we have three diagonal matrix where the main diagonal elements are just repetitive, x1, 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 x2, 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 and then x3, x3, x3. Okay, so now we have the full picture. I know how to compute the gradient all the way up to the input layer, right? So now you can see that I have 3 by 3 by 3 by, the result is 3 by 3 by 3 by, okay, I just ignored the dimension 1. Okay, 3 by 3 by 3. So I would have computed all these things, right? By now, before reaching this part, now I have computed all these things. What will be, let me say the final result is denoted as stored in a vector u. Okay, so what will be the size of this vector now? Because I computed all these things now. Can you see the size, the dimension of this vector now? Or am I asking a difficult question? What is the dimension? So it's 1 by 1, 1 by 1, 2 by 1. So it will result in 2 by 1. So it will also give me 2 by 1. Then it will result in 3 by 1. Then finally 3 by 1. So I would have one, okay, after computing all these terms, right? I have one vector of size 3 by 1 with three elements, u0, u1, u2. Okay, now I have a tensor. Okay, so keep this, I try to connect. Okay, so I mean, as if I have a matrix, just to see how tensor product works, if I have a matrix and a vector, and then of course you can write this equation, see ij is equal to sum over all these elements, but pictorially I take this row vector and multiply its column vector, I will get a single number, then I pack, this is the first, the output is a single number, so I place it in as a first element. Then I take the second row and then multiply with the column vector, again the output is a single number, then I place next to it. So finally I end up creating a vector. Okay, so when you multiply a matrix by a vector, the result is a vector. What I have now is I have a tensor, okay, 3 by 3 by 3 tensor, and then a vector, okay, 3 by 1 vector. So similar to how you took this dot product between the row vector and a column vector, you can take a product, a matrix vector multiplication for each of these three matrices. Okay, I first take this matrix and multiply with u0, u1, u2. What will be the result if you multiply it? What is the result?
It will again tensor.
Tensor, okay. So you can see that I'm just writing down elements so that you see the picture clearly. u0 x1, u1 x1, u2 x1, right? Because I have only diagonal matrix, it's only scales the thing, right? Do you agree with this one? After multiplying the first matrix with the vector u0, u1, u2, sorry, all these elements, this will be the result is going to be a vector with the values u0 x1, u1 x1, u2 x1. Does it make sense?
Yes, sir.
Okay. Then what will be the next column vector? Because now I multiply this second matrix with the vector, so it is going to be u0 x2, u1 x2, u2 x2, and then the third is going to be u0 x3, and then u1 x3, u2 x3. Okay, so can you write this down as an outer product of two vectors? How do you write this? Can we write this as an outer product of two vector?
Yes, there will be a row vector for u0 and a column vector for x1, or reverse.
Okay, so since I keep this u0, u1, u2 as a column vector, okay, this is how the input is. Then what will be, so which is of size 3 by 1. Then I transpose the input, okay, x1, x2, x3, right? It's 1 by 3. So which is simply the incoming gradient after computing all the previous step. That is what u0. That is in fact how dou L changes with respect to whatever. Maybe I think it is dou A1. Okay, or whatever. So we are computing gradient and finally we end up this value. Okay, and then we take the transpose of input and we multiply, you will end up with these values, which is 3 by 3. So all these things are a gradient of weight vector W. This is a gradient for the weight vector W0, sorry, for the parameter W00, W01. So whatever the dimension of your parameter in the input layer, the same thing. Okay, so this is exactly similar to what we have done in the, what we have derived in the lecture. Okay, but by paying attention to the individual elements and then we reconstruct everything. Now we did the same, but now we took the matrix with matrix approach, matrix calculus approach per se. Okay, when things become complicated, I hope this is clear, right? Now there are three processes. You take gradient with respect to a scalar and a scalar, and then compute the partial derivative with respect to a vector, and compute the partial derivative with respect to a vector, and then a matrix. now you know how to do that. And of course, putting things in perspective or in a proper order takes some practice, so you will recognize them quickly. The key takeaway, okay, so if you understand this whole process, so next I'm going to talk about BPT, where I would like you to remember this. So if I have a linear computation where A is equal to W times input X plus B, then if I want to compute the gradient, okay, with respect to this A, okay, sorry, I would say it's a local gradient, okay, how A changes with respect to X, okay, and of course following all the denominator layout. So if I ask you what is dou A by dou X, then if you follow the denominator layout, then it is going to be W transpose, okay. You just remember this. This is one of the key things we keep repeating, okay. And when gradient flows through the activation function, it is simply an element wise product. That's not a big deal, okay. So you just remember this. I'm going to make use of this fact when I compute BPTT, okay. So if you know, just ensure that you got all the concepts that I just discussed so far, okay. Shall I move on to BPTT?
Yes, please.
So I made a small presentation, but not much with animations. I know it's going to take time, so I just made it. So you just remember this result. I'm going to make use of this result. Just display the result, and of course, I ask you whether you understood that part or not. Okay, so let me. This. Okay, are you able to see the presentation?
Yeah.
Okay, so I think, okay, I don't know whether I'm able to write it. I'm not able to write it. So give me a second. Okay. In fact, I made a presentation for CNN, but I just ignored it. Instead of helping you, taking some time. It's a bit slow. So, I'm sorry, I think it's taking too much time to load. Are you able to see the animation? I mean, displaying one part at a time. Oh God, if you press, it takes some 3 to 4 seconds. Oh, it has gone so. Okay, give me a second. I close the rest of the operations. It is that might be unnecessarily delaying things.
Sir, have you already discussed the RNN?
No, I'm just going to start.
Okay.
Okay, so in RNN, what really happens is that you just think it of a cell. I have a W matrix that always gets multiplied with my previous state vector, okay, st minus 1. And then I have a matrix U that always gets multiplied with the input at current time step. And then I'm adding it together. I consider it as an individual operation. Okay, this is a linear operation. I mean, just a matrix vector multiplication. I represent the result in Z. Instead of using A, I am using Z. Okay. Now I take this output, which is the result of these two linear matrix vector multiplication, and then I pass it through an activation. It could be anything, but in general it is tan H. Then I take the output, I denote this as ST. Okay, this is for simple RNN. So this ST is used in the next time step. It is also used in the current time step based on the problem. We just generalize this. Okay, if it is as you know, it's a translation system where we use ST in each intermediate step. But if it is a classification, then we use ST at the final step. Okay. So if you are using at the intermediate step, then I also use the another matrix V that takes in ST. I'm once again breaking it down. Okay. This is a linear operation, matrix vector multiplication. So I store the result in another variable. So let's say it's RT. Then I pass it through a sigmoid function. It's not integral. So it's a sigmoid function. Then I compute the probabilities. Then we have YT hat and YT. Then we compute the loss. Okay. So this is what this is. Once if you understand this procedure, then we don't even look at computing the gradient throughout the time step. Let's compute the gradient at one time step and then simply repeat the process. Okay, so this is a forward prop. What happens in the back prop? Okay, so I discussed all these things. Let me just
Will you repeat the previous slide again, just quickly?
Previous slide. This one. Sorry,
the first one. I mean,
this one.
Yeah, this. Yeah.
Okay, I think let me write down the equation. Oh, I'm not able to annotate. I'm not seeing anything. Okay, I'm very sorry, I'm not able to write. Okay, anyhow, I hope you remember that equation ST, right? So we compute ST is equal to tan H of W times X1, sorry, W times ST minus 1, the previous, and then U times the input, right? So the same thing, I'm just creating a picture out of it, okay? So I have an RNN cell where I have the matrix W. This matrix W is shared across time steps. So this W will always gets multiplied by the state vector at previous time step, okay? And then similarly, I have a matrix U which is shared across all time steps, and this U will always gets multiplied by the input at current time step. Then I take this result, which is a linear operation, I store it in a variable ZT. Then I pass this to a nonlinear activation function. Okay, it could be anything, it could be tan H or whatever. Then result of this nonlinear activation is a state vector HT. Okay, I mean state vector at current time step. Then I make use of this current time step. I use this state vector at current state step in the next time step, and I could also use this vector for some prediction. Okay, in the case of translation, we do predict the next word. Okay, for each time step, there will be an input as well as an output. But in classification setting, for each time step, we simply compute the state vector. For at the final time step, we make use of the state vector at the final time step, and then we compute the output, whether it's a positive or negative class. Okay, so we have to use another matrix V, which takes in the state vector st, and then I compute V times st. I store it in an intermediate result RT, because I'm going to pass it through a softmax. Then I pass this through a softmax. Softmax give me the prediction. If it is a at every time step it predicts the probability of the word. Okay. Then we have yt hat, and then I have the true label yt, and then we compute this, and then we compute loss, right? LT. So this is the for.
Yeah. So can we take an try example and unpack it, because I want to understand it thoroughly. I mean, is it okay if we have enough time?
Okay, so I mean, this is a particular time step in RNN, right? So we have an RNN where we unroll the RNN for each time step, right? Let's say I have a word, I'm going home, right? So if it is a translation system, what we do? I first pass I, and then am, and then go, right? One word at a time. So in this case, you can think of xt is a word at current. I'm unable to write. I don't know why.
I mean, can you download the PPT and then you can use that whiteboard?
No, that's not actually. That doesn't work with this slides.com. Fortunately, I got this. Okay, so here xt t could vary from I am going home. So there are 4 words. So t could vary from t 1, 2, 3, 4. I will have 4 time steps, right? So at first time step t is equal to 1, my input word is going to be I. So I have representation for I, then it gets multiplied with the vector, the matrix U, and then I have an input state vector Sj. I initialize the input state vector S0, and then that gets multiplied with W. Then this is a matrix vector multiplication. This also a matrix vector multiplication. I store the result in Z. Okay, then I pass. This is going to be a vector, right? This is a vector. Then I pass it through a tan H, compute the values element wise. Then I compute S1. Okay. Then I take this S1 to the next time step. Okay. In the next time step, the same thing will repeat. Only now t is going to be 2. So you substitute all these values. So before moving on to the next time step, if it is a translation system, I also take this st and pass it through another matrix, because I have to translate it, right? So to do that, I take the same vector. It's a kind of, you think of it as a T junction, where I split this into 2 parts. So one, I forward this st to the next time step, where it gets multiplied by W. Meanwhile, I forward this st to this matrix V. Okay, so it gets multiplied by V, and you will get once again a vector. Then you pass it through a softmax. Then you will end up with Y0. So Y0 is simply, if it is a translation, then I means, I don't know, in Tamil it is non, right? In Hindi, what is that? It's mujhe. May. Okay. So is that right? May. M-E-Y or M-A-Y?
Same thing. Doesn't matter.
Okay. So I want to predict this particular word out of all the words in the vocabulary, right? So I want to predict the probability for all the word in the vocabulary. So for that, I'm using the softmax. Okay, softmax gives me the probability for all the word in my vocabulary, where I expect the probability for ma is higher than the rest of the probability for the rest of the words. Okay, so that's what the softmax does. Then I take the true label, and then I compute cross entropy in this case. Okay, so this happens for the first time step. In the next time step, then my word is am instead of I. Then st is going to be s1, and then the same matrix are shared across time step. W remains same, U remains same, V remains same. Then prediction might differ. Okay, with the proper translation, right? So is this clear now?
Yes.
Okay. Okay, this is the forward propagation through time for a single time step. Okay, then let's focus on.
Sorry, Arun, at that stage, when we have done one time step,
Yeah,
what can we salvage from that whole thing which will help later in backpropagation? Just LT, right? Because when
yeah,
we compute loss, it will be summed up against all of the time steps.
yes.
But my W, U, and V will have changed later, correct?
Later means
At time step T.
see time step one
No,
I
no,
have
no, sorry.
WV. So for all the
Exactly.
time step, W will remain same. I won't compute the gradient at this time step.
Oh, so I'm not doing any backpropagation here.
No, I won't. You can do back prop, but you won't update the weights.
You won't update the weight. So for backprop at this stage, what can we keep aside? Nothing, just LT. Other than
Yeah.
LT,
So
nothing, right?
it's like after time step one, you could compute the gradient of W with respect to LT. You mean you can compute the gradient for all V, W, U. You just keep it.
Okay, okay.
And the next time step, once again, you compute all these gradients. Let's say it is, what to say, it's with respect to your loss for a particular word. So in each time step, you can compute the gradient. You can keep it. But while we do back props through time, then we keep accumulating these gradients before doing these weight updates.
Fine.
Okay. So this we have discussed so far. Okay, so here I am not following any particular, I mean, even though I follow a particular layout, I just follow the command instead of writing everything from the reverse order, which often confuses people. I just go with whatever the order we prefer. We can simply change it. Okay, so of course we have to start from, let's focus on a particular time step T. It could be the last time step or it could be the first time step. We don't care. We just focus on a particular time step T. Now I have computed the loss. Now I have to compute the gradient of the loss with respect to yt hat. We can compute that. It is just -1. You can work it out, right? So this turns out to be -1 by yt hat. And then you can compute the loss with respect to the input. What is the input to the softmax now? It is RT, right? So what is the, for softmax, once again, you can see, right? So this is true even in feed-forward neural network. If this is a softmax, then it is going to be simply you just take the prediction and you subtract it from the true label. That is the gradient for the softmax. Okay. So now I have dou LT by dou RT. Okay. But what I want is the gradient for the matrix V, which is dou LT by dou V. Okay. So how do you compute dou LT by dou V? So how they are at the first hand related. So if you write down this equation, right, first LT depends on RT and then RT depends on V. Remember, if I follow denominator layout, I have to switch these terms to have proper multiplication. But once again, I'm just writing for clarity. Okay, so I have computed this dou LT by dou RT here, which is YT minus Y. Okay, so YT is just the prediction at time step T. So the T where you don't need to focus on this symbol T at all. Okay, it's simply y hat minus y. Then you need to compute how RT changes with V. So RT is now a vector, okay, and then V is a matrix. Okay, now I am telling you, right, and remember, an ST is also a vector. Okay, you just expand all this matrix vector multiplication and work it out. Okay, it turns out to be ST transpose. Like we have W and W transpose. W was a matrix there. Here S is a vector. Now vector gets transposed. Okay. Unless you work it out, you can't see why it is getting. It is simply ST transpose. For now you just take it for granted. You are able to compute that, and it turns out to be ST transpose. I have computed ST already, so I make use of it. Okay. I won't do update now. I just computed the gradient. I keep it. Okay. Because the same thing I have to compute for all the time step, and then I have to accumulate the gradients. Okay, so of course for W it is not depending on all the time step. And okay, so now I have computed dou LT by dou V, gradient for V. But what I really want, I want the gradient for W and gradient for U. Okay, so how do I go about it? Now I have value for dou LT by dou V as well, dou LT by dou RT, and dou RT by dou V. These are all, the gradients that we are simply computing along this pathway. Okay, so it's not really a big deal. Okay, now let's move on to the next. Okay, I'm just focusing here a bit. The next variable is st. Okay, so we are computing this. I have to compute how loss changes with respect to, because each of these outputs are going to affect my loss. Okay, that's why we are computing dou LT by st. And of course, once again, we start from dou LT by dou YT hat. Okay, all this term, this is for this YT minus YT hat, and this one is V transpose. Okay, we can check that as well. So I just multiply this, and then I will get dou LT by dou ST. Okay, which is an state vector at current time step, because state vector also influences my the loss at time step t. Okay, now I have to, the next step is quite straightforward. Now I have to pass this through an activation function, which is once again an element wise product, right? So you pass it through an activation function, so which is dou LT by dou ZT, input to that activation. Okay, so that turns out to be, even though the equations are getting bigger and bigger, I'm just adding new terms. Okay, this is already there. I just added this term. Okay, which is the derivative of the activation function, which is tan h. Okay, now I have these terms computed. I have it in my hand. Now I have to make use of this, and then now I have a plus symbol, so these things will get splitted. The next step is I have to make use of this in order to compute the gradient for W. Okay, you just you remember this. I'm just explaining. This is the newly added term, nothing else. Now we have to compute here. Okay, so what is that? How my loss change with respect to W? Remember, I have already computed this term dou LT by dou ZT, which is the entire equation here. I have to compute dou ZT, which is a vector with respect to this W. Okay, and if you compute that, it turns out to be ST minus 1 transpose. Okay, and the additional term is, now with all these terms, I just need to multiply ST minus 1 transpose. Okay, so the current gradient, okay, the gradient of the loss LT with respect to W depends on all these factors. Okay, YT minus Y, of course you can plug in the
Sorry, could you repeat that, Arun?
which
Current gradient
from
as
where?
in at what depends on all these factors?
The gradient of W at time step t.
Okay, yeah.
I mean, the gradient, I mean, we keep computing this gradient for each time step, right? So even though I don't, I mean, it's redundant to put t here. So I'm just telling the gradient at time step t for W.
At any time step, yeah. Fine.
Yeah. So, so this simply progresses, right? And once again, I repeat the same, I will end up with the same equation. Instead of, for U, I will, instead of ST minus 1, I will end up with the XT transpose. Okay, so that is going to be the only difference. Now, the few more steps are that I have to pass this gradient to the previous, I mean, how do I say? So during the forward prop, I have multiple cells. Okay, now I am at time step t. I computed the gradient dou LT by dou W, and then I just store it. And then I also have this dou LT by dou ZT, and then dou LT by dou ST. Okay, so I need to pass this to the previous time step. Okay, that's where the accumulation happens. So I first focus on a single cell. I compute all these things. Then I have, like in the forward prop, I compute ST, right? I take ST minus 1, I compute ST, and then the process gets repeated. Here I compute dou LT by dou ST, and then I have to pass it to the previous time step. Okay, so that, okay. So just focus on this picture. Now we have computed dou LT by dou W. So what will happen in the next step? That's the question. What are the things that I need to accumulate? That's the question. Okay. Okay. I am first read this, whether you understand this. So, if you are not able to get this particular wording, then I need to change that. Okay. So when I hand over this material, maybe that might be helpful. Okay. So what I am trying to convey here is that we are computing this gradient at particular time step t for w, but this w and u v are shared across time step, right? Especially this w is shared for all the state vectors across time step, but u and v are just depending on the input at particular time step, but w is kind of shared across the entire time step, right? So how do I put it into words? So there is a gradient coming from my previous time step. So I'm just using this t plus 1. Okay. I would have computed this in the previous time step, right?
But why do we care about adding this? Because later anyway we are going to sum up individual, like okay, let's say that we just care about W's right now, gradient for
Okay.
W's, right?
Okay.
So anyway for LT plus 1 I'll compute the same thing again, right? So why do we care about this thing coming in right now?
No, the thing is that for this loss, my ST is influencing the current loss LT, but the same ST is also influencing my final loss, right?
Yes.
So we can do
And
one.
whatever that influence is will show up in the next time step car loss, correct?
That's what this term denotes, right? So this says that the loss at the next time step is also depend on the state vector at the previous time step. So I have to backprop it, right?
Okay, I think once you continue, it will become clearer. Please carry on.
No, I mean, before continuing it, I should explain this because I haven't put much in the next slide. So
We can, sir, one thing here. Suppose we reach up to the ST, right?
yeah,
Here only two thing we can, if think, then rest of thing is the just recursive, and that two thing is that one ST we can differentiate with respect to DW, which is just behind the ST. Second, ST we can differentiate with respect to ST minus ST minus 1. This two thing is will recursively. So this two thing if you will get, everything will be easier then.
no, I'm not getting exactly what you are trying to convey.
This ST is there, right?
Yeah,
So,
this ST you mean?
no,
Or this one or this one?
yeah,
Okay.
yeah. So can you mark this? So this ST go ST1 up to throughout the S0, right?
Yeah, so in this direction, yes.
It go.
Yeah.
So this and the W will be also recursively go many W, right?
Yes.
Behind ST1 also one W up to the S0 there will be W.
Yes.
We can do one thing here when we go back propagation. So two thing is important. One st divided by dot dw, which is the just below of just previous explicitly.
Mm.
One and second is the dot st divided by dot st minus 1. Only these two things will be there, and dot st1 t minus 1 itself will do the same process. So if you
So
will
you
divide,
mean
yeah,
computing dou and dou st by dou st minus 1.
right. One is that, and another is dou st divided by dou w. And whenever I say this dou w, that is not the and w. It is just before w, means explicitly w.
Okay, I'm not sure whether that works. Okay.
in the third lecture also he tried to do that thing, but at the end lecture got lecture slide, it is a stop there. So derivation is not fully clear the way you are explaining the nicely up to the dl by that, sorry, dl by the dst, dlt by dst is the clear.
Yeah.
Now there is a two derivation is left, dst by dst minus 1 and dst by dw. Everything is
So,
complete.
the first place, do we need to really compute do st by do st minus 1?
Yes,
Okay,
yes.
by the way, let's
Because
take
that
it to the.
because derivation changes here.
Okay, so but when we go component wise, right, I'm really okay. I'm not sure whether that really fits in, but uh, let's discuss that later. I mean,
Okay.
we need to discuss a lot because RNN is quite involved.
So
So what I'm trying to do is that, remember, throughout all these steps, we are computing everything with respect to the loss. Okay,
yes.
so loss at time step t depends on v and then st at time steps t. Okay, but when I go to the next time step, okay, so let's say I have lt plus 1. There lt plus 1 depends on, of course, somehow this st is encoding all the previous st's, right? So in the next, this is, sorry, I would have another cell here, then I call this as st plus 1, then that pass through the same v, and then we compute the loss, right? So this st plus 1 encodes st and all the previous time step, st minus 1
So
and then
so
st minus 2.
got it, sir. So that is not important because it is the loop plus recursive is there. So the only these three steps is only doing everything. So that thing can solve using recursive, but only these three thing is important. And after these three thing, we can recursively add all the thing.
Mm-hmm.
So already you have done LT divided by DST1. Only the
Yeah.
two thing is left, DST by DST minus 1 and DST by DW, just behind the W.
Okay. Okay. So anyhow, I think.
Up to here it is
Yeah.
clear. It is, if and then next class we can keep it.
Okay, so I think now I have computed, the gradient of loss at time step t with respect to w. So how do I propagate, or what should I propagate to the previous time step? Okay, so in the
Then yes, sir. Please.
I mean, okay, so I'm just trying to connect these. Okay, in unrolled version we have something like this. I have st plus 1. That's what I'm propagating, right? St minus 1. So w connects all of these things. So let's say I'm at time step t. This is the final time step t. Okay, so I compute the loss here. So now I compute all these things. Let us presume t is equal to t here. Okay, so in this entire derivative, let us assume t is equal to t, the final time step. So I compute the loss here. I don't have anything to add. I just follow at final time step t. I compute all these things. Okay, and then I finally have this picture. So it's t is equal to t. I computed all these things. Finally, I also have computed dou lt by dou w and dou lt by dou u. I would have computed this and then dou lt by dou v. So it's a final time step. So I'm using time step t. Okay, and the
Sorry, just a second. It's at the bottom right, the expression that you have,
yeah,
that
this one.
for no, bottom left, sorry, not bottom right.
Okay.
The first term on the right hand side, which is S superscript T, that is transpose, not nothing to do with T equal to capital T.
Oh, no, that's not t is equal to,
Okay,
it's a transfer.
thanks.
Okay, okay, so it's final. Oh, maybe what? Maybe I can use t is equal to tau then. Okay, so if it is final time step, everything makes sense. Okay, if this is my final time step, I could compute all these things, and now I have dou lt by dou w. Okay, now you just see what really I mean, how I got this st minus 1. So in the I got this st minus 1 from the previous time step, right? Then there will be same v, and then I would have softmax here. Then I have what is that? I compute L tau minus 1. Okay, tau is the final time step, and then this is just the previous time step. Okay, and this is here, right? Now I'm just repeating. I have the same activation function. This is st minus 1. This is also st minus 1, and v is also multiplied by st minus 1. Okay, so so the justification for this one, right? Do lt plus 1. That is, when I try to, I don't know how to put that into words. I mean, the only way that we connect these two time step is through st, right? So for that reason, I need to compute this loss with respect. So in this case, it is tau by do st minus 1. Okay, so I need to compute that. That we can compute it using the same formula. I mean, same approach we have used here. So I just display the next two equations, see whether it makes sense. Okay, so this is, I'm just telling, this is coming from, this is a recurring thing. So this loss is also, the loss with respect to the current time step is also getting in. So I have to make you remember, this is just a this is scalar and this is vector. So I would have computed this quantity and it is just getting in, and I made one operation here, right? That operation is like splitting these two, okay, or kind of making this into, I have one operation where I made this split. Okay, so the gradient, local gradient is coming from this current time step as well, and the loss at t plus 1 is also coming from this path. So this gradient has to be added. Okay, so you take time.
Arun, let me see if let me try and explain it, and maybe you can point out the fault in the way that I am trying to understand it. So again, let's focus on the gradient with respect to W, gradient of the loss with respect to the W matrix.
Okay.
We have that expression at the bottom left. There is no t plus 1 term there.
Where do you see? Do
At the
LT by
bottom
do,
left,
yeah.
do LT by W, there is nothing which is subscript t plus 1, correct?
Yes.
Which means that this gradient is dependent only on the current time step. Now, if we
Yeah.
have to add something, does it mean that that particular expression is incomplete or what?
No. Here, how should I mean, I didn't display the gradient for this LT plus 1 here. It is like, maybe I share this slide, you go through it. Tomorrow I show you the code. Okay. So
Okay.
that, maybe that makes sense why I am adding this term here. Maybe I might have used some improper notation, but
I think, sir, here the differentiation will split in the two way. One, d st dou st by dou w is the one term, plus add the dou st by dou st minus 1, and that dou st minus 1 will follow the same process is the right now. So the left term, whatever that you have written, dou lt by dou w, so it is stopping just before the zt, right?
stopping, yeah, it got incorporated in this
Yeah. So
step.
so it should go through up to that up to the end. Just
Up to the end means up to zero time step.
S0.
Yeah.
So there is that's why. So we need a recursive. That portion we can think recursive. So at this
Yeah.
point there will be two things will split. At the ST there will be two differentiation will split. One will go toward the ST minus 1 and one will go direct toward that DW means W.
Yes. Okay, I added this plus term, so I'm just thinking about how to explain this. Okay, Jada, I think the best way is to, when I show you the code, right?
Okay.
Then it makes sense. But just remember this: this is already computed. Okay, so which means I need to compute this quantity which I'm going to compute for this time step. Okay, so I have to compute this dou LT by dou ST. That's what I computing here. Okay, dou
Okay,
LT
okay.
by dou ST man. Okay. So which is simply a W transpose time dou LT by dou ST. This quantity will be back propagated.
Right. Yes.
Yeah, I think now it makes sense, right?
Yeah, yeah.
Upper will be back propagated.
Yeah,
Below
so
will get stopped.
yeah. So yeah, why we need to compute this quantity? Because ST minus 1 is also influencing all this YT.
This is what is referred to as the implicit part of the
Yes,
gradients, is it?
yes.
So
But
yeah, that was my original question. That particular expression is not complete. You have, maybe for the sake of convenience, not written the implicit parts. Only explicit is written here.
yeah, here everything is explicit. But when we do this recursively, then
Yeah,
things will be
understood.
merged. Yeah. So now it's like if it is a last time step, there won't be this quantity, but in the next time step, I make use of this and then add this with this. And then I keep repeating this process again and again. So if I write a code now, then I have to write a code to compute all these quantities at a particular time step. And then I just need to propagate this to the previous time step. I just keep adding this gradient. Okay, the loss with respect to a time step t. Okay. Yeah, I think, yeah. Okay, so when is the due date for this assignment, by the way? Is that
Day
over?
after tomorrow. No, this one is over.
Okay, so I shared the collab for this RNN then. Okay, then you may take
Wait,
a
wait,
look
wait.
into.
I may be mistaken.
I
There's
think in
something day
week,
after tomorrow.
yeah, I think week 10 assignment is over, right?
Yeah, this
Week
is
10
week
is
10. So
where,
yes, it's over. Yeah.
yeah, and I think in week 10, I am asking you to compute, asking you to make a classification or a translation. I'm not sure.
Same thing. DL by dot W.
Okay. Okay, then I share the collab for week 10. You take a look at the code.
It is classification. The word is learn, one hot encoded, and you have to predict the next character.
Yeah, yeah. Then that's fine. Then I share the collab, then you can build on top of it. Okay, I mean, this is quite involved, by the way. We have to be, kind of careful and do some test cases and, you know, ensure that the gradients are properly computed and see whether the loss decreases by running the algorithm for some 10 iterations or so. Okay. Yeah, so I find it difficult to explain as well because many things are connected. And as you know, if you follow this approach, you need not to bother much about this tensor product or such. Okay, so if you look at the entire expression of RNN, then it is intimidating because you try to. It is like you are trying to form a closed form solution. Okay, which is quite kind of impossible even if you try to form the closed form solution. Okay, but if you break it down for a single step and then if you are able to write a code for a single step where you compute all these gradient uv for each step and then update the weights, but for w just shared across time step, then I think it is quite okay to write the code conveniently. Okay, but anyhow, I shared these slides. uh, Please cross check whether the implementation is correct and work out. I'm sure, I think all of these things are properly computed because I ran the algorithm for 10 or 20 iteration and see whether it converges, but still there is a chance I could have made some mistakes. Okay. Okay, so I think this is one of the longest live session, not one of the only longest live session, I guess.
But it's good, sir. The most of thing you clear that, and it's most of thing clear. Only one thing will go again.
Yeah, sure. Yeah, Kumar, sorry. Please go ahead.
No,
What?
it's clear. Everything you made that clear at the beginning session, 1 hour itself. The most
Yeah.
problem was there in the differentiation and creating the tensor. But tensor will go once more. If any doubt is there, then we will ask in chat.
Yeah, sure. Please do that.
And it's clear now, much of.
Okay. That's
So one more request, Arun. I want to take 2 examples. One is for the CNN and one for RNN, and solve them by hand. And I'll post my solutions on Discourse.
okay.
Could you go through them and verify if they are right?
Yeah. Please do share it.
Well, the CNN example I take from Quiz2 itself.
Okay. Yeah. Please post the solution, then I tell you whether that is right or wrong. I think already one student posted the solution for one question, I guess. He shared his handwritten notes.
And that solution was able to get all the correct answers as marked in the answer key?
So, which one you are pointing to?
That solution which was posted.
Yeah.
That got all the answers right according to the answer key?
One answer is right. One the weights are correct, but for the bias he made some mistakes. But he didn't write.
That's where I'm also stuck. So that's why I was saying. Anyway, I'll go through that post.
Okay, sure. Okay, you post it. I cross check it. Okay, then. Thanks for joining. I hope maybe you feel comfortable with BPTT after 1 or 2 weeks. Okay,
yeah,
then
after 1 or 2 weeks, the term is going to be over.
Yeah, that's why I'm saying. Then you will be relaxed, so you might, go through one step at a time.
Okay. Yeah.
Okay, I shared the link for the recording in the Discourse, or I updated in the calendar. Okay, link.
Just in case, maybe also put it up on YouTube so that it will be there for others on the channel.
Oh, we can upload it, right? Okay.
Yeah.
Okay, I upload it in the YouTube then. I think that's better. I upload it in YouTube and share the link. Okay, bye everyone then.
Thank you. Thanks a lot, Arun.
Thanks so much.